We've already talked about the definition for half-life. Remember, half-life is symbolized by T1/2. The half-life is the time that it takes for the concentration of a reactant to decrease to half of its initial concentration. We've also already talked about the integrated rate law, or the integrated rate equation for a second-order reaction. So here's one form of it. 1 over the concentration of A minus 1 over the initial concentration of A is equal to the rate constant K times the time. So if we're talking about the half-life, so that would be when time is equal to T1/2. So we're going to plug T1/2 in for the time. What's the concentration of A? Well, using the definition for half-life, the concentration of A should be half of the initial concentration. So our initial concentration would be this, so it's half of our initial concentration. So we're going to plug that in to here. All right, let's plug those in and see what we have. We have 1 over the initial concentration of A divided by 2 minus 1 over the initial concentration of A is equal to the rate constant K times the half-life. So on the left side, right, this would just be 2 over the initial concentration of A minus 1 over the initial concentration of A is equal to KT1/2. So what is 2 over the initial concentration of A minus 1 over the initial concentration of A? That would just be 1 over the initial concentration of A, and that's equal to the rate constant K times the half-life. So now we can solve for the half-life. Just divide both sides by K. So we get the half-life is equal to 1 over K times the initial concentration of A. And so here is our equation for the half-life for a second-order reaction. Notice this is very different for the half-life for a first-order reaction. For a first-order reaction, we saw that the half-life was constant, but here the half-life isn't constant because the half-life depends on the initial concentration of A. And let's look at a graph of concentration versus time for a second-order reaction so we can understand this concept a little bit better. So when time is equal to 0, right, this point right here on the graph would be the initial concentration of A. So here is our initial concentration of A. And let's just do a made-up reaction here. Let's say we're starting with 8 particles or 8 molecules. So here we have 1, 2, 3, 4, 5, 6, 7, 8. Right, so if we wait for the concentration to decrease to half its initial, right, what are we left with? We'll be left with 4 molecules. Right, so we're left with 4 molecules. So I'll draw those in there. And how long did it take to go from 8 to 4? Right, we can find that on our graph. If this point represents the initial concentration, right, half that would be right here. That would be the initial concentration of A divided by 2. So we find that point on our graph, and we drop down to here on the x-axis, and it took 1 second. Right, so our first half-life is 1 second. So let me write that in here. So this represents our first half-life, which is 1 second. How long does it take for the second half-life? So how long does it take to go from 4 molecules to 2 molecules? Let me go ahead and change color and be consistent here. So we're going from 4 molecules to 2 molecules. How long does it take to do that? Well, if this is our starting concentration now, what's half of that? So on our graph, half of that would be right here. And this would represent the initial concentration divided by 4 now. So here's half of this, and if we go over, we can find this point on our graph, right? So the point on our graph would be right there, and we drop down, and we can see we're at time is equal to 3. So how long did it take this time for our half-life? This time our half-life would be 2 seconds. Right? Our half-life is 2 seconds. It's twice the first half-life. And we can understand that by plugging into our half-life equation over here. Right? So if we say the first half-life is 1 second, right? So if we say the first half-life is 1 second here, let's go ahead and plug in for the second half-life. So the second half-life would be equal to, So it'd be 1 over the rate constant K. But now our initial concentration, right? Our initial concentration is not the initial constant, is not this, right? It's this. It's the initial concentration divided by 2. Right? So I'll go back over here. This would be the initial concentration of A divided by 2. So for the second half-life, this would be equal to 2 over K times the initial concentration of A. And we can see that that is twice this up here. If this is our first half-life, which is 1 second, this is twice that, which of course would be 2 seconds. So this makes sense, both looking at the graph and also thinking about the equation for our half-life. So our second half-life is twice as long as the first, and each half-life is going to be twice as long as the one before it. So if we wait one more half-life, so the third half-life, we're going from 2 molecules to 1 molecule. So now our starting concentration would be right here. So what's half of that? That would be right here. So we go over and we find this point on our graph. All right, so we find that point on our graph right about there, and we drop down and we can see the time is equal to 7 seconds. So what's the third half-life, right? This would be the third half-life right here on our graph, and obviously that would be 4 seconds, right? So 4 seconds, which is twice the preceding half-life. All right, so let's see if we can figure this out a little bit more. So what does this mean? This means in the early stages of your reaction, right, you have a higher concentration of your reactant, right? And the higher concentration means that those molecules can collide better, and so therefore the reaction goes faster. And so if we have an increased concentration, we have an increased reaction rate, right? Therefore, the faster the reactant is being consumed, and therefore the shorter the half-life, the shorter the time it takes for the concentration of the reactant to decrease to half its initial concentration.